Yeah. So, hi everyone. Uh, Before I start my presentation, I would like to say that previous presentation was a really good segue into what I'm going to be presenting here. And my presentation is mainly focused on the work that we're doing as part of the 6GXL project and the design of the AI controller. So we actually took into account the conflict mitigation as well in the design itself. But please keep in mind that the AI controller design is an initial design, and there's a lot of space for extending it and even replacing bits and pieces. And I'm going to be talking about those parts throughout the presentation. So just a quick reminder, this is our DMM AI framework that we all came up with together. And the core bit of the whole framework is the AI controller that needs to be flexible and modular in a way so that we could deploy it on different network nodes and basically just to enable different AI control applications to run on top of those nodes to basically control the nodes themselves, but also to enable the communication between different AI controllers so that they can exchange either information or decisions that they make on different parts of the network. So far, we've been focusing on the control of the nodes themselves and the interaction between multiple nodes in the network, multiple domains in the network, but we completely ignored the communication with the orchestrator, and that's something we can discuss further, maybe later today or tomorrow. So the current system architecture consists of 6 modules, 2 APIs, so the Node API and the Inter AI API, 2 message brokers, and an AI-powered control engine, and the Node control module. So let's just have a quick look. So when we started thinking about the design itself, we didn't just put a bunch of elements on a whiteboard and then connected them to each other. The first iteration was, let's have a look at the near real-time RIC and what already exists over there. What works well, what doesn't work well, what's too complicated maybe for a simple AI controller. So we didn't want to build another RIC. We wanted to build a lightweight framework that can be extended, but it's not rigid. So you don't have to take all of the modules and deploy them on every single node, because in the run we have the near real-time RIC. We have a lot of compute power. It's basically meant for running AI applications. But then in the transport network, we have some nodes that don't have a lot of compute power. They wouldn't have a lot of memory. So we have to keep in mind that the same AI controller, or at least a lightweight version of the AI controller, should be deployable on those nodes as well. So we started with 2 message brokers, and the idea behind the message brokers was to have a microservice-like architecture that allows us to completely disconnect different parts of the architecture so that, for example, a node that doesn't need to communicate with other nodes can just deploy the node broker, but it doesn't need to deploy the inter AI broker. So the main idea behind these message brokers is to enable asynchronous compute within the controller and on the controlled node itself. So the idea behind the topics, for example, on the north-south communication, is that each topic represents a different type of measurements that's being exposed by the node. And we're being very generic here because topic 1, topic 2, topic 3, they could be SNR, could be the CQI if we're talking about the radio access network, but could be the OSNR in the optical part of the network. So those topics can be whatever we make them, so that different measurements can be exposed from the nodes and basically digested by the controller itself. On the right-hand side over here, the inter-AI message broker is used for the communication between different AI controllers. And those topics, again, they could be bits and pieces of information. For example, if we want to expose some of the features that are used by the AI controller with another AI controller, they could be used as topics to exchange those. But in a federated learning the kind of use case, they could be used to expose weights of the models that are being used by the AI controller so that the weights can actually be shared between multiple controllers to converge to a global setup. And we've seen some presentations today on federated learning. We've also seen some presentations on controlling networks. So the next building block of the controller would be the AI-powered control engine. And this engine, it serves multiple purposes. The main purpose here is to provide a framework for AI control application. They provide a framework for us to deploy different AI control applications. So it's basically an environment. You can think of it as a container that has all the software tools pre-installed, and it has connections. Like it basically implements publish-subscribe communication pattern between the two different brokers, allowing us to digest, to basically ingest all the messages that, all the measurements that get exposed by the controlled node, and to expose different control messages. So whenever an AI control application needs to control a node, that control message would be, for example, published on topic 5, and then the node itself would subscribe to that topic. And then whenever there is a control message up there, it would take that control message and do something with it. So the next building block is obviously a set of AI control applications. So we wanted to build an environment where multiple AI control applications can exist, similar to what we have in the near real-time rig. So we can run multiple accepts on the near real-time rig. But then Richard just nicely introduced an issue that's related to what happens if multiple AI control applications try to control the same knobs in the network, or they don't even have to control the same knobs, but they might have an impact on similar performance measurements. We don't need to control the same parameters, but I don't know, if we want to optimize for throughput, we might end up losing on energy efficiency. So in order to be able to kind of even understand what's happening with the control applications, and if there are some conflicts. So the ORAN Alliance introduced 3 different types of conflicts, like the explicit ones when they're touching the same knobs, which are very, very easy to detect. But then there are those implicit ones that are very, very hard to detect. And at the moment, from what I've seen from the research papers out there, the idea is to use another set of AI applications to try to detect those types of conflicts. But the idea behind our project, 6GXL, is not to, let's say, go deep into solving those problems. It's rather about providing a framework that provides all the information necessary to do research on all of those topics. And that's why we introduced a register. So the register is a necessity not just for conflict mitigation, it's also a necessity for any type of controller that needs to control a network node. Because let's say we have a node that exposes a set of measurements. We have 2 base stations, two, let's say one built by SRS, the other one by OAI, and they don't expose all the same measurements. And we've already seen that with the E2 interface. It's a well-defined interface and everything, but then the controllers don't communicate very well with the base stations themselves. And I believe that if any one of you has ever tried to build an XApp, it's much harder than we sometimes advertise it to be. So the idea behind the register is that whenever a node that's going to get controlled by the controller wants to connect to the controller, it registers all the performance measurements that it is capable of exposing and all the control messages that it actually accepts. And then at the same time, whenever we spin up an AI control application, it needs to register with the AI control app register. And what it basically does, it says, okay, I want to control this specific node. And my input is going to be this set of performance measurements. If that set of performance measurements is not exposed by that node, the AI control application should simply fail, because not every node exposed with the same set of performance measurements. At the same time, the AI control application needs to say, I'm trying to control these specific knobs on that node. And if those knobs are not controllable by this specific node, again, the AI control application should fail. And we should get a message saying, well, you can't control these things, or you can't read these performance measurements out of the network. So this is the baseline architecture of the controller. But then as part of work package, I think 3, and I apologize if it was 4 or 2, but as part of the discussion with especially Juniper, we realized that we need to define a specific set of APIs for the communication between the different AI controllers and the nodes and the control application as well. So the idea is to basically build an API in front of both message brokers that's going to be used to register the node, register another AI control application, and expose different functionalities. For example, creating different topics. If a node wants to register with this specific controller, it's going to say, I'm exposing this specific set of performance measurements, so please create all these topics that another AI control application could basically subscribe to later on. And please expose all these control parameters that I accept and create topics for those as well. And then whenever an AI control application wants to control those knobs, it should post the control messages on those specific topics. So this is the architecture that we have at the moment. As you can see, it is still missing, especially the parts for the communication with the orchestrator. And we are planning to build on those. But we already started implementing all these parts, and at the moment they're implemented as Docker containers. So we already deployed them, some of them in the radio access network, some of them in the passive optical network. And obviously, as I said, not all of the nodes can actually implement everything, or sometimes it doesn't make sense to implement everything. And the idea behind the controller is, yes, it should be an AI-powered controller that allows us to control the network by using different AI applications. But it doesn't have to be AI necessarily. It can be any kind of control application. And you will see a couple of slides that I'm going to share later on that describe an OFC demo that we had earlier this year, where we used components from the controller to establish the communication between the radio access network and the PON to minimize latency in the network. So here you can see all the parts that I mentioned of the controller. So these six parts of the controller. I don't have to go through these slides explaining the node registration and when a registration fails or not. Let's move on to the OFC demo. So we've deployed, as I mentioned, we've deployed bits and pieces of the AI controller already in our testbed, and we're testing them at the moment. So the demo that we presented at OFC, the idea behind the demo was to have a DU and CU somewhere at the edge, and then to have a PON between the DU and the RU. For the OFC demo, we were missing some components. We were especially missing a PTP switch, so we couldn't go with the split 7.2. We went with the split 8. So we basically had a USRP over here. And then through the Tibit, we were basically building a small passive optical network, and the PON exposes control interfaces through the CTI interface. And then the idea was to, whenever a user wants to send something in the uplink, it obviously talks to the scheduler on the DU, trying to get some resources in the uplink. Whenever the scheduler receives a request from the UE, it would share, like whenever it makes a decision, so the decision is going to travel downstream towards the UE, but at the same time, the DU would share that decision through the CTI interface with the PON controller. And then the PON controller could reserve resources in the uplink before they're even needed in the PON. And the whole idea behind that was to accommodate ultra-low latency services so that the traffic that's coming in the uplink doesn't get buffered in the PON. It basically just travels through. So we presented this demo at OFC, but just to show you like a block diagram of how everything actually looks like, we used SRS run for our implementation. So SRS implements this PAPI interface, which is an interface between the high physical layer and the MAC. And all the messages that are related to the MAC layer basically travel through this interface, all requests in the uplink and all decisions in the downlink. So the best place to basically tap in and read any requests or any responses was actually at the FAPI interface, but it's a very sensitive interface because it's very delay sensitive. So we tapped into that interface. We added parts of the AI controller. So there was no AI involved in this demo specifically. It was basically just about the communication parts. So the north-south and east-west part of the communication. And then we would expose those measurements from the FAPI interface to a message broker that was deployed as part of the CTI interface, where the CTI interface, the PON controller, would basically subscribe to all the messages coming from the radio access network. And whenever there's a request for scheduling resources, the CTI would expose those requests to the PON controller, and the PON controller would schedule resources at this interface, basically at the Tibit OLT. And whenever something was traveling uplink, it wouldn't get buffered at all, and it reduced latency. I can't remember the numbers. You can look up the paper if you're interested in that. I can share the paper later. That was quite successful, but then we tried to basically map our AI controller onto it. So the AI controller could basically sit within this controller, which is the PON controller itself. And it would basically establish a communication with the near real-time RIC. In this case, we didn't use the near real-time RIC, but this is more kind of an idea to extend it further and implement some AI-based applications. We added this kind of storyline as part of one of the use cases that was collected by IMEC as part of Work Package 2. And the main idea here would be to develop an AI application that would try to, let's say, predict the upstream traffic, because this traffic, it's not just the traffic coming from an RU, it's also traffic coming from fiber to home users or any other users that are connected to the PON. So if you try to make predictions about the amount of traffic that's actually coming towards the PON, you could make smarter scheduling decisions in the PON itself. But at the same time, the radio access network needs to have some level of priority if you want to repurpose the PON for radio communications. And then the idea would be to do a similar estimate on the near real-time RIC to try to predict the amount of traffic that's incoming. And that those kind of predictions can be more precise when it comes to the radio access network, because we can make predictions about the handovers that are happening. We know how much load balancing is happening in the network. So we have more information on the radio access network about the traffic that's flowing through the radio access network, which is quite obvious. And then by sharing the information between the RAN and the PON, we could improve the predictions that the AI controller is making over here. And the idea would be to develop such a use case as part of the 6GXL project. So that would pretty much be everything that I wanted to share as part of this presentation. Thank you.
Okay, do we have questions in the audience? Over here. Hey, Merim, can you hear me?
Yes, but if you don't mind, just speak a little bit up. Yeah.
Okay. First of all, thank you so much for the presentation, right? But I want to ask you one thing, right? When dealing with such a distributed setup, right, with a bunch of different moving parts acting on different resources, how do you deal and mitigate with conflicts?
Yeah. So, I mean, as Richard said, it's not an easy solution, but the idea here is to expose everything that's controllable, like basically the whole action space, and to expose the operation of every AI application. So in this case, we're looking at one controller. And if we look at mitigating the conflicts within a controller, you could run a separate AI control application that would read all the messages from the register, understand what all these control applications are controlling, read all the performance measurements, and let's say have a time series kind of data set available within the register, and understand that when two applications are controlling a certain set of parameters, they're basically fighting against each other. That is still hard, but quite a bit easier if it's within one controller. And I agree that it becomes even more difficult if you have a distributed setup. But then again, we do expose everything from the register and the AI control applications through these topics over here. So it would be, in my mind at the moment at least, it would be a hierarchical setup where you would have, let's say you have two of these controllers talking to each other and making decisions separately or cooperatively. But at the same time, you would have a third, you can call it a controller, but it doesn't need to be a controller. It can just be a third entity that can read messages from all these topics and from the topics from the other controller, basically exposing, again, everything that's being controlled on both sides and what's happening with the performance metrics over time. By understanding what's happening with the performance metrics over time and with everything that's being controlled, you basically have all the information needed to understand where the conflict's coming from. I'm not saying that you can still identify what's creating the conflict, because here I'm simplifying the whole scenario by saying you have only two controllers, because Richard was completely right when he said that the problem isn't trivial at all, because it is going to be very hard to identify if you have multiple controllers controlling elements of the network that are not completely independent. But the idea so far, I mean, not my idea, the idea within the research community so far would be to have another AI entity that would be able to identify those conflicts.
I guess a conflict manager could be, I think, as the Northeastern guys have some conflict manager that they developed.
The Pacifista, that was a good paper. I didn't know that that Richard was involved in that work, though.
So that could be deployed into this framework, for example, right? Or I wonder, your AI conflict manager, could that also be an XApp or RHAP, I guess?
Thanks a lot, Merim. It's a very complex problem, this consistency problem, if you look at it from the general case. I will advise you to, not you in particular, but I think for GXL, if you look at the paper published by Google at Usenix Orion, which is basically how they manage the infrastructure with a hierarchy of SDN controllers. At the end, they need to have a global state somewhere. And they consolidate within, they call it information-based, network information-based or something like this. So, I mean, either you put constraints, as Dan said, if you want to play an app on an iPhone, you have constraints, you cannot deploy whatever you want, or you need to basically consolidate somewhere. So I don't think you can solve the problem otherwise. That's my two cents.
Yeah, I agree. Thanks.